Hey everyone, and welcome to today's Explainer. So, today we're going to take something that most of us just think of as this totally chaotic, unpredictable natural disaster, and we're going to flip that perspective completely on its head. We're talking about earthquakes, but we aren't just going to focus on the shaking ground or the terrifying stuff that happens on the surface. Instead, we're actually going to look at earthquakes as the ultimate scientific tool. Because, believe it or not, they are literally Earth's invisible X-ray. They send out these signals that allow us to basically peer deep down inside the mysterious, totally inaccessible layers of our dynamic planet. It's wild. To understand exactly how this giant planetary X-ray works, here's our quick roadmap for today. First, we'll look at the anatomy of an earthquake. Second, unlocking Earth's hidden interior. Third, the global shadow zones. Fourth, 5 types of quakes. And finally, measuring impact and tsunamis. So we're basically going to descend all the way into the deepest hidden parts of the Earth and then travel all the way back up to the surface. Let's dive in. Section 1, Anatomy of an Earthquake, the Invisible Mechanics. Before we can really wrap our heads around the visible destruction that happens up here on the surface where we live, we first got to look at the microscopic, unseen mechanics happening deep underground.
Okay, so when an earthquake happens, it generates waves. And these earthquake waves are basically broken down into 2 main types, body waves and surface waves. Now, how these body waves behave as they travel through the Earth is just absolutely fascinating. As they move through underground materials with different densities, their velocity actually changes. So the denser the material, the faster the wave moves. But it goes even further than that. Because the density is changing, the actual direction of the waves changes too. It's kind of like how a straight beam of light bends and distorts when you shine it through a glass of water or a crystal prism. Earthquake waves do the exact same thing. They reflect and refract as they hit different geological materials. And it's this continuous bending, bouncing, and echoing that actually creates our planetary X-ray.
Let's break down those body waves a bit more because they come in 2 very distinct flavors, P waves and S waves. P waves, or primary waves, are the absolute fastest. They are always the first ones to arrive at the surface. They act a lot like sound waves, which means they can travel through completely different environments, gases, liquids, solids, you name it. Imagine you have a classic metal slinky. If you push it forward, the coils compress and stretch in the exact same direction you pushed, right? Well, that's how P waves vibrate. They move parallel to the direction of the wave, creating pressure that literally stretches and squeezes the rock they pass through. Then we have our S waves, or secondary waves. These arrive with a bit of a time lag because they're slower, and they vibrate perpendicular to their direction of travel. Picture taking a really thick rope and snapping it up and down. The wave moves forward, but the rope itself is moving vertically. That up and down shaking, that's an S wave. But here is the most crucial distinction of all, the absolute game changer for science. S waves can only travel through solid materials. Which brings us to Section 2, Unlocking Earth's Hidden Interior, the Great Geological X-ray. This is exactly where those unseen mechanics turn into an incredible diagnostic tool for scientists.
Now, this brings up a really fascinating central mystery. Think about it. If no human being has ever dug anywhere near the center of the Earth, we've barely even scratched the crust with our deepest drill holes, how do we actually know what's down there?
The answer lies in that one absolutely crucial characteristic we just talked about. S waves can only travel through solid materials. When an earthquake sends these secondary waves echoing through the planet, scientists all over the world are carefully monitoring them on seismographs. And because S waves absolutely cannot travel through liquids or gases, if those waves suddenly just stop transmitting as they go deeper, well, that gives us the ultimate clue. That sudden, dramatic stop tells scientists exactly where the solid materials of the Earth's mantle end. And guys, this is precisely how humanity made one of the greatest geological discoveries of all time, the realization that the Earth has a molten, liquid outer core. The sudden disappearance of those S waves provides the exact boundary line of that subterranean ocean of liquid metal. It's like finding a wall in the dark just by listening to the echo. Moving right along to Section 3, the global shadow zones, Earth's massive blind spots. So, we know waves bend, and we know S waves get stopped cold by liquids. But what exactly happens up on the surface when the Earth's interior blocks or redirects these waves? To understand this, we need to quickly define a highly specific geological term. A shadow zone is a specific area on the Earth's surface where seismographs do not record the arrival of earthquake waves at all. Scientists use seismograph records to figure out the variations in the direction of the waves, but in a shadow zone, the instruments simply don't register the arrival of those deep vibrations. The waves have either been blocked entirely or bent completely away from that location. It is quite literally a planetary blind spot.
And scientists have mapped exactly where these blind spots occur relative to where an earthquake actually started. They observed that seismographs located at any distance within 105 degrees from the earthquake's epicenter successfully recorded the arrival of both P and S waves. However, they found this specific, massive global boundary between 105 degrees and 145 degrees away from the epicenter. That area was identified as the shadow zone for both types of waves. And to put that into perspective, we aren't just talking about a small patch of land here. These degrees represent thousands and thousands of miles of the Earth's circumference, where the planet goes completely seismically quiet. The P waves are bent sharply away by the liquid core, and the S waves are just absorbed and blocked entirely.
This beautifully illustrates the sheer, massive scale of wave refraction and blockage inside our planet. While the P-wave shadow zone is just that specific band between 105 and 145 degrees, the entire zone beyond 105 degrees does not receive S-waves at all. So the shadow zone of S-waves is much, much larger. In fact, it covers a little over 40% of the entire Earth's surface. No way, right? That is an awe-inspiring amount of the globe just left completely in the dark, sitting in a seismic blind spot. That 40% shadow is the definitive invisible shadow cast by our planet's own molten core. But as absolutely fascinating as this deep Earth X-ray is, the energy does eventually reach the very top layer. As our source material dramatically puts it, the surface waves are the last to report on seismograph. These waves are more destructive. They cause displacement of rocks, and hence the collapse of structures occurs. This perfectly bridges our narrative today. We're rushing back up from the deep Earth, past those body waves, to the really chaotic surface impact. The unseen mechanics we've been talking about have now translated into highly visible displacement and very real human consequences.
Which brings us to Section 4, 5 types of quakes, categorizing the chaos. Because while destructive surface waves feel exactly the same to anyone standing above them, the actual triggers for these events are surprisingly different.
Yeah, earthquakes don't just happen for one reason. They're triggered by a variety of distinct geological and actually even human-made phenomena. There are 5 distinct categories. First up, tectonic earthquakes. These are the most common kind we usually think about, caused by sliding fault lines. Second, volcanic earthquakes, which are directly tied to active volcanic eruptions. Third, collapse earthquakes. These happen in areas of intense, large-scale mining where massive underground roofs suddenly cave in. And surprisingly, we also have strictly human-made events. Fourth on the list are explosion earthquakes, which are generated by the detonation of chemical or nuclear devices. And finally, fifth, reservoir-induced earthquakes. These occur in areas where massive artificial dams have been built, causing the sheer immense weight of the stored water to trigger fractures in the rock way down below. Crazy, right? Now for Section 5, measuring impact and tsunamis, scales and oceanic aftermath. Here, we're going to focus on how humanity categorizes, measures, and really understands the visible results of these geological events once they reach the surface. When an earthquake strikes, the events are scaled in 2 primary ways, and it's super important to clearly contrast them. The Richter scale relates purely to the sheer, invisible energy released during the quake, which is expressed mathematically in numbers from 0 to 10. In contrast, the intensity scale, named after the Italian seismologist Mercalli, takes into account the actual visible damage caused by the event, and its range goes from 1 to 12. So simply put, the Richter scale measures the mathematical energy of the quake at its source, while the Mercalli scale measures the physical destruction it causes to our towns and cities.
And of course, we really cannot talk about visible destruction without clarifying one of the most powerful aftereffects, the tsunami. A tsunami is defined as waves generated by tremors, and this effect only occurs if the epicenter of the tremor is below oceanic waters, and the magnitude is sufficiently high. It's a really crucial distinction to make. Tsunamis are waves generated by the tremors, not the earthquake itself. The earthquake is the trigger, the tsunami is the massive oceanic aftermath. So we have traveled from the microscopic mechanics of stretching and squeezing waves all the way deep into the Earth's solid and liquid interior, through the massive 40% shadow zones, and back up to the collapsing structures and oceanic waves right on the surface. It really completely changes how you view these events, doesn't it? So I want to leave you with this thought. Next time the ground shakes, will you just feel the surface destruction, or will you picture that massive planetary X-ray happening deep below your feet? Thank you so much for joining me for this explainer, and keep exploring the fascinating mechanics of our dynamic planet.